Okay, so we're going to prove some properties of finite sums. So for any n contain the natural numbers and sequence a sub I from 1 to n, b sub I from 1 to n, and a constant c, we know the sum of these two sequences is equal to the sum of this sequence plus the sum of that sequence. Same thing with the difference. And if you have the sum of a constant being multiplied by the sequence, it's the same thing as that constant times the sum of the sequence. So um, let's go ahead and start with number one. So proof, right? So number one, we're going to look at the sum from 1 to n of a sub I plus b sub I. And we're going to try to show this, right? So this is equal to, so using the definition of sum, this is a sub 1 plus b sub 1 plus a sub 2 plus b sub 2 plus dot 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 plus a sub n plus b sub n. And of course, using the associative property, we know we can change this to be a sub 1 plus a sub 2 plus dot 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 plus a sub n plus, and then we'll put all the b's together, right? B sub 1 plus b sub 2 plus dot 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 plus b sub n. And the sum of these n's is literally this. It's the sum from 1 to n, right? From 1 to n of a sub I plus, and this sum from 1 to n, right? The sum from 1 to n of b sub I, which is exactly what we wanted to show, right? We wanted to show that the sum from 1 to n of a sub I plus b sub I is the sum from 1 to n of a sub I plus the sum from 1 to n of b sub I. Now we're going to look at the difference, right? So 2, we're going to look at the difference between those is equal to the sum of this minus the sum of that, right? So let's go ahead and do the same thing. So the sum from 1 to n of a sub I minus b sub I, that's the same thing as a sub 1 minus b sub 1 plus a sub 2 minus b sub 2 plus dot 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 plus a sub n minus b sub n. All right, so now I know I can put all the a's together and all of them are positive, right? So this is equal to a sub 1 plus a sub, oh, that's not an a. A sub 2 plus dot 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 plus a sub n, and then plus, and all these b's are, they have a minus in front of it, right? So plus negative b sub 1 minus b sub 2 minus dot 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 minus b sub n. And what we can do with those is we can actually factor out the negative, right? So first off, this is the sum from 1 to n of a sub I, right? So this is the sum from 1 to n of a sub I. And then I'm going to factor out this negative, right? So minus b sub 1 plus b sub 2 plus dot 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 plus b sub n. And that is exactly what we wanted, right? Here, well, let's go ahead and finish this. So this is the sum from 1 to n of a sub I minus the sum from 1 to n of b sub I, right? So we've shown that the sum from 1 to n of a sub I minus b sub I is equal to the sum from 1 to n of a sub I minus the sum from 1 to n of b sub I. Okay, so the last one we want to show is that the sum from 1 to n of c times a sub I is equal to c times the sum from 1 to n of a sub I. So let's go ahead and do that here. So 3, the sum from 1 to n of c times a sub I. Well, using the definition of sum, this is the same thing as c times a sub 1 plus c times a sub 2 plus dot 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 plus c times a sub n. And just like with the negative in the other one, right? Since all these terms share a constant c, I can factor out that c. So this will be c times a sub 1 plus a sub 2 plus dot 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 plus a sub n. And of course, that is just the sum from 1 to n of a sub I. So c times the sum from 1 to n of ace of I. And that is the proof, right? We proved all of these properties for finite sums, right?